This lecture was organized by Dr. Alemi. It focuses on various probability mass functions, including Bernoulli, binomial, geometric, and Poisson distributions. We show how these are related to each other and how they can be used to describe real processes in healthcare settings. A function assigns numbers to events. A probability density function gives the probability of a group of events or a single event. On the x-axis is the categories of events of interest arranged from low to high values. On the y-axis is the probability of cases that fall within the category. In contrast, the cumulative function gives the probability of all events less than or equal to a specific level. Both functions, both density and cumulative functions, require us to sort events from a low value to a high value. In this example, the number of medication errors are sorted and listed to the left. The first column shows the probability density function. At each value, it provides the probability of the event listed. For example, 90% of patients have no medication errors, 6% of patients have one medication error, and 4% have two medication errors. The cumulative distribution function is also given in the right column. It starts at 90% and increases or stays the same thereafter. The cumulative distribution function gives probability of occurrence of all of the events with values less than or equal to the event. For example, 96% is the probability of having patients with 1 or 0 medication errors. The steps in a cumulative distribution functions are equal to the probability of the event at this step. Probability density functions can be used to calculate the expected value for an uncertain event. The expected value is calculated by multiplying the probability of the event by its value and summing across all events. The probability of event I occurring is multiplied by the value of event I and summed over all possible values of the event. Here we show this as sum over event I going from 1 to n. Here is an application of the formula to a sample data. In this example, the number of medication errors are sorted and listed to the left. The first column shows the probability density function. At each value, it provides the probability of the event listed. For example, 90% of patients have no medication errors, 6% of patients have one medication error, and 4% have two medication errors. To calculate the expected value, first we multiply the value of each event by its probability. In the first row, 0 medication errors is multiplied by 90% chance to obtain 0. In the second row, 6% is multiplied by 1 to obtain 0.06, and 4% is multiplied by 2 to obtain 0.08. The expected medication error is the sum of the products of the event value and its probability. In this example, we expect 0.12 medication errors. We can see this example visually as well by charting the density and distribution functions. Let's focus on the following data. And suppose we want to calculate the expected number of medication errors. We begin with calculation of the cumulative function from the density function. A cumulative function shows the probability of events less than or equal to a particular value. It never decreases. At each step, we add the value of the density function to the previous value of the cumulative function. The expected number of events is calculated as sum of the number of events times the density functions. This chart shows visually the probability density and the cumulative distribution functions. The size of the step in the cumulative distribution is the same as the probability of the event. For example, the rise from 0 to 1 medication error is equal to the probability of 1 medication error. The shape of the distribution function tells a great deal about the function. For discrete variables, the type of data we focus on in this course, there are some very unique distribution functions, each with a signature shape. Knowing the probability density function is a very important step in deciding what to expect. Naturally, a great deal of thought has gone into recognizing different probability distributions. The most common density probability functions for discrete variables are Bernoulli, binomial, geometric, and Poisson functions. We will describe each of these functions and explain the relationship among them. These functions are useful in describing a large number of events, for example, the probability of wrong side surgery, the time to next gunshot in a hospital, the probability of medication errors over a large number of visits, the arrival rate of security incidences, and so on. If our focus remains on events that either happen or do not occur, then these four distributions are sufficient to describe many aspects of these events. Bernoulli distribution function is the most common discrete density function. It assumes that two outcomes are possible. Either the event occurs or it does not. In other words, the events of interest are mutually exclusive. It also assumes that the possible outcomes are exhaustive, meaning at least one of the outcomes must occur. In a Bernoulli density function, the event occurs with a constant probability of p. Typically, it is assumed that the probability is calculated for a specific number of trials or a specific period of time. For example, we can talk of probability of patient elopement in our facility to be 0.05 in a month. 95% of patients do not elope in any single month, but 5% do. This chart shows both the density and cumulative probability distribution for these data. The red line shows the cumulative function, and the bar graph shows the density function. Let us now think through a situation where a Bernoulli event is repeatedly tried. Let us assume that in these trials the probability of occurrence of the event is not affected by its past occurrence. In other words, that each trial is independent of all previous ones. As we will see shortly, when we are dealing with independent repeated trials of Bernoulli events, a number of common density functions may describe it. Let's look at an example of repeated independent trials. In this situation, we have 3 repeated trials for tracking patients' elopement over time. We are assuming that the probability of elopement does not change if a patient has eloped in the prior months. In month 1, the patient may elope or not. In month 2, the same event may repeat. The process continues month after month until month 3. As you can see, the patient may elope in different months, and on each month this probability of elopement is constant and equal to prior months. Independence cannot be assumed for all repeated trials. For example, the probability of contagious infections changes if there was an infection in the prior time periods. Therefore, independent trials cannot be assumed for contagious infections. But in many situations it can, and when we can, there is a lot we can tell about the probability function under this assumption. If a Bernoulli event is repeated until the event occurs, then the number of trials to the occurrence of the event has a geometric distribution. The geometric density function is given by multiplying probability of one occurrence by probability of k minus 1 non-occurrence that should precede it. An interesting property of geometric probability density function is that the expected number of trials prior to the occurrence of the event is given by dividing 1 by the probability of the occurrence of the event in every trial. If we know that wrong side surgery has occurred only once in last decade, how many surgical days before we can expect another wrong side surgery? See if you can calculate these probabilities. Here is another set that might be interesting to work out. Assume that we repeat the Bernoulli trials and that each time we do so the probability of occurrence of the event stays the same, and it is independent of what has happened in the past. The binomial density function gives the probability of having k occurrences of the event in n Bernoulli trials. For example, having 2 patients elope in 3 months is possible if patients elope in month 1 and 2 but not 3, and if they elope in months 1 and 3 and not 2. Finally, the third possibility is that the patient elope in month 2 and 3 and not 1. The probability of elopement is p. The probability of not elopement is 1 minus p. The probability of 2 patients eloping in the first 2 months is given as p squared times 1 minus p. The 1 minus p refers to the patient that did not elope in the 3rd month. The probability of elopement can also be used to calculate the probability of exactly 2 patients eloping in the first 2 months, and this is p squared times 1 minus p again. The probability of exactly 2 patients eloping in the last 2 months is given as 1 minus p times p squared. The probability of 2 patients eloping in the first and last month is given again as p squared times 1 minus p. This exercise with elopement has shown how binomial distribution is constructed. There are 3 components. The first component is the count of different combinations of getting exactly certain number of occurrences and non-occurrences. In the binomial formula, n exclamation mark is referred to as n factorial. The proportion of n factorial divided by k factorial times n minus k factorial counts the number of different ways k occurrences of the event might be arranged in n trials. The second component is the probability of the event to power of number of trials with the event, in this case k. The third component is the probability of non-occurrence to the power of number of non-occurrence. The term 1 minus p to the power of n minus k measures the probability of n minus k non-occurrence of the event. Now we can look at some examples so you can have an intuitive understanding of the binomial distribution. Here you see a binomial distribution with 6 trials. There are 7 possibilities. Either the event never occurs, or it occurs once, twice, 3 times, 4 times, 5 times, or 6 times. The probability density function shows the likely occurrences. The most likely situation is for the event to occur 3 times in 6 days. This is also the expected value and can be obtained by multiplying the number of trials by the probability of occurrence of the Bernoulli event. Let us now go back to the patient elopement example, where the monthly probability of elopement was 5%. Over a 6-month period, we are most likely to see no patient's elopement. There is a 23% chance of seeing 1 elopement, and there is a 3% chance of seeing 2 elopements. Now we can answer also this exercise more fully. If the daily probability of elopement is 0.05, the expected number of elopement over 2 years is probability of elopement times the number of trials, in this case 24 months. If the daily probability of death due to injury from a ventilation machine is 0.02, what is the probability of having 1 or more deaths in 30 days? Here the number of trials is 30 days. There is only one combination of getting 0 deaths, so the factorial term is equal to 1. The probability of survival is 0.998, and we expect 30 days of survival. The probability of death is 0.002, but we expect no one to die. So the probability of 0 deaths is given as 0.942. So the probability of having 1 or more deaths is 0.058. See if you can answer this question by yourself. As the number of trials increases and the probability of occurrence drops, Poisson distribution approximates binomial distribution. In healthcare management, this occurs often. Typically, we are looking at a large number of visits or days, and the sentinel event has a very low probability of occurrence. In these circumstances, the number of occurrences of the event can be estimated by Poisson distribution. In this formula, lambda is the expected number of trials and is equal to n times p, where n is the number of trials and p is the probability of the occurrence of the event in one trial. K is the number of occurrence of the sentinel event, and E is 2.71828, the base of natural logarithms. So the take-home lesson for this lecture is that repeated independent Bernoulli trial is the foundation of many discrete distributions. See if you can answer this question. Also try to answer this one.